quiz that we're going to look at later, which is similar to some of the concept questions that you might see on the final. It doesn't have a lot of math in it, but if I'm going to ask 46 questions, a lot of them are going to have to be kind of quick answer things, because I can't just give you a bunch of really tough problems. But it also gives me an opportunity in the final to test you on a wider range of subjects than I would if I were just randomly selecting problems. And it's also easier for me to evaluate course objectives if a problem's either right or wrong. And so that's one thing I have to do is see whether or not you're learning the subjects, and which subjects are you learning, which ones aren't you learning. And so, if you get 6 out of 10 on something, it's more difficult for me to evaluate that. But if it's right or it's wrong, that gives me more hard data to work with. Also, there are a lot of exams, like the GRE, that are purely multiple choice. And so I think it's good that you do have a feeling for how to work with a multiple choice exam. In terms of fixing your corrections, by giving 15 points might be a little overly generous, in that at least a half a dozen people will get over 100% doing that. But I think they probably deserve it. One problem in particular that I was a little disappointed with was the capacitor problem, because I covered that 3 times in lecture. I did that first with the Gauss's law for a cylinder. We plotted the results. I did it again when we did the electric potential. I worked that whole thing out again, worked out the electric potential. Did it a 3rd time when we calculated the capacitance. And I taught physics at Cal Poly for 10 years, and if I gave that kind of a coverage of something, I'd be getting 90% of the class we were getting right. And that didn't happen. So I'm disappointed, and I hope that you realize that you're not going to be competitive with people who are planning on transferring to Cal Poly with that kind of performance. But if you can do really well on the final, I could possibly downweight a midterm if you had like one bad day. And I could see that you did really super well on the final. Not an exact science, but let's say that all of your midterms were like super A, except for one, which was a D or something, and then you got another really strong A on the final, then I might tend to overlook that one bad score. So that's more motivation for you to try to do well in the final. So what I'm going to be doing this week is going over basically chapters 30 and 31. There'll be a little bit of 33 on Thursday, but I'm going to hold off on doing a lot of 33 until Physics 2A to C. Because using Maxwell's equations to get the speed of light is critical to understanding special relativity. And there's not as much time as I would like to cover all of these subjects in Physics 2A to C. I'm going to talk a little bit about the formation of electromagnetic waves, but I'm not going to go through the same kind of math detail that I will as the first subject when I cover it in 2AC. So what we've looked at so far is different applications of Faraday's law in this new material. Faraday's law tells us that the induced voltage is the time derivative of the magnetic flux, where the magnetic flux is equal to the integral of B dot dA, very similar to electric flux. But if the magnetic field is constant over the area, then this reduces to just B dot A, or BA cosine theta, where theta is the angle between the normal to the area and the magnetic field B. So this, we've looked at what magnetic flux is. We've also seen before that it's really the same definition as electric flux. So hopefully you had that set of subjects in hand, and this is really just an application of the same mathematics. But there are quite a few applications of this, and I've covered a lot of them already, but I want to do a few more because there's really a lot going on with this. A lot can be applied to it. And so in my first example, what I'd like to do is take a look at a simple problem where we've got a loop. Let's say it's a square loop instead of a circular one. Square loop of length L on the side. Is oriented so that the plane of the area is parallel to the magnetic field. And then let's say that L here is 1 meter and B is 10 to the minus 2 Tesla. Let's now rotate this in 1/10 of a second so that now it is oriented so that the plane of the orbit is perpendicular to the magnetic field. Let's find the average induced EMF. Okay, so to get average induced EMF, what we're going to want is E average is going to be minus delta, I'll call it delta flux over delta T, instead of d flux dt. Okay, so this is the total change in flux over 1/10 of a second divided by that total amount of time, which is 1/10 of a second. Okay, and so the instantaneous voltage is going to be a function of angle, because at each new angle, you're going to have a different effective cross-sectional area for the loop. And so that's a little different than this problem. In this problem, I just want the average induced voltage during that rotation period. And as I rotate this thing, I'm going to feel a resistive force, because I'm going to have to do work to get that current flowing through. Okay, and so if we plug into this relationship then, it's one of the simpler applications. We can say that this is going to be B times A minus 0 divided by T. Okay, so in this case, we've got BA cosine 0 degrees. So that's our flux final. And our flux initial is what?
0.
0, because the angle is 90 degrees. There's no magnetic field cutting through those, that loop, because it's going parallel to the plane. So when I was saying here that the square loop is oriented so that the plane is parallel to B, that's not the angle that we're talking about. But that's what a lot of people like to think the angle is. And so that's why I wrote it that way, just so that you get this feeling that, no, I can't just accept that. What I have to do here is draw my unit normal and then define the angle in terms of that unit normal. So that needs to be your first step in this problem, is to turn this into something where we can use the equations that we have here and not assume that this thing is going in such a way that, because we've got an undefined direction. If it's in the plane of the loop, it could be anywhere within the plane of the loop. So that's not a precise description of what's going on. But this is going to be flux final, which is BA, minus flux initial, which is 0, divided by delta T. Okay, so it's not that hard of a problem to do. This is really one of the more simple, basic problems to do. It's almost a concept problem, in that you just need to know what's being represented by each of these terms so that you can put it into the appropriate relationship. So this is just B. In this case, that's 10 to the minus 2 Tesla times A. So that's going to be L squared. That's 1 meter squared divided by T, which is 1/10 of a second. Okay, so that would give us here 10 to the minus 2, and then this is the same as multiplying by 10. So that would give me 10 to the minus 1 volts. So that would be my average induced voltage over that 1/10 of a second time period, or 0.1 volts. Are there any questions about that? Okay, well, let's go to a slightly more challenging problem. In this problem, and this is one of your handouts for today, we have a bar of length L right on the screen. I always do this. Okay, so this bar, let's make, so that's of length L here. So this bar is length L, and it's sliding down conducting rails. And those conducting rails are immersed in a uniform magnetic field that's acting vertically. Okay, and so this thing then, let's assume there's no friction, because if there's friction, then we've got a more complicated problem, but complicated for the wrong reasons. I don't need to get back into Physics 208A problem, where you've got a lot of extra math that isn't really emphasizing the point that we're driving home here. So I'll simplify the math by saying that that conducting bar is sliding down this conducting rail at an angle theta. So this is like going down an inclined plane, but with no friction. So because it's a conducting loop, and that conducting loop is getting smaller in area, we can say, well, then we're going to have a induced voltage that's going to be, the magnitude of that induced voltage is going to be d flux dt. Okay, and so the flux then is somehow related to this area, but the unit normal to the area is pointed at an angle essentially theta with respect to the magnetic field. Okay, and so the unit normal then here, respect to the magnetic field, is oriented at an angle theta. And so that means that the flux then is going to be BA times the cosine of theta. And so when we do d flux dt then, what we're going to get is, well, we know that B dot A is BA cosine theta. Okay, so we have derivative with respect to time of BA cosine theta is just going to be equal to B times L times dx dt times the cosine of theta. We think of this distance here as being like our x distance down the incline. Then dx dt is going to be our velocity down the incline. Okay, and so this will be equal to BLV cosine theta. Now remember when we were moving this thing in a loop like this, we showed before that the magnetic, the force, I'm sorry, we were talking about the change in the flux, so that was the induced voltage, was BLV. We did this problem before where we had a magnetic field like this, and we showed it was BLV. So here it's BLV cosine theta because the effective area is different. It's the projection of this area onto this horizontal surface here. So that area is A cosine theta. Or this area here is A, but the effective area relative to that magnetic field is A cosine theta. And so that's why that cosine theta term comes in here, because it's like the shadow of this area. You know, as we're looking down on this thing, we could have sun rays coming down like this and projecting a shadow onto that surface. And so that shadow would have an effective area that's A cosine theta. So that's how our flux is defined. So that's one of the terms that we need. You need to know what the induced voltage looks like. And also, we have to have an equilibrium in forces. If we want the equilibrium velocity, then that's the same thing as our terminal velocity. Okay? And so that means that this thing is going to be accelerated down the incline at mg sine theta, but it's going to start to pick up speed as it goes. But as it picks up speed, that velocity produces a bigger voltage. And associated with that, we get a bigger magnetic force. So how does that force work? We want the forces to balance. So what we can say here then is that, here's the equation for the balanced forces. This is all written down for you in your notes. And so we've got ILB cosine theta. So how do we get that? Well, if the current is moving this way, ILB, then the force is going to point straight away like that. Okay, so it's going to point straight this way. So that means it's going to have two components. One is going to be perpendicular to the surface, and one's going to be parallel to the surface. And so we want the one that's parallel to the surface. Now the perpendicular one would be useful if we had what? We would care about the F sine theta component if what other condition happened. If we had friction in the problem, then the normal force would be altered by this, and that would affect the force of friction. And so that's what makes the problem more complicated if we go that way. But we don't need to go that way here, because I think we're illustrating the point well enough without friction. So all we're really interested in then is the F cosine theta component of that force, and at equilibrium, this is going to generate a bigger and bigger current until it finally equals mg sine theta. Okay, so the current then will continue to grow. This is the induced current in this system. And that induced current fights the change in magnetic flux that produced it. Okay, so where do we get that from? Well, we know that our induced voltage is equal to IR. So that means that we have one more step here to solve for I. So I is going to be BLV cosine theta over R. And then we can plug that in here for I. Once we have that I, we can plug it in there. And so that's what I did down here. I feel the cosine theta over r. So then I'm just taking that I, I'm plugging it in there. So I've got I times LB cosine theta equals mg sine theta. Then I collect together like terms in B and L. Here, I'm using smaller case L here. I was using larger case L before. The reason why I like the smaller case L's is that we're about to introduce an inductance, self-inductance, and that's big L. So we don't need a lot of extra L's that are in the same case floating around. So I'll just call it little L. So we plug that in, and then we can solve for the velocity, and that's just mg sine theta times the resistance. That's the resistance of the loop. And now that resistance will change as the distance around the loop changes. So let's assume that in the rest of the loop, the resistance is negligible, so that most of the resistance is just in that bar that's sliding down and not in the rest of the conducting rails. Then we don't have to worry about the area changing the resistance, or the length of the wire, I should say. The circumference of that square or rectangular loop won't affect the resistance if we have all the resistance in the upper bar. So we've made a few assumptions here, because then you've got a complicated thing going on. If the area and the length of the thing is changing, then that changes the R. So that's dependent on time. And so all of a sudden this problem becomes much more complicated. We start throwing in those kinds of real life situations. And so this then gives us our final expression for the velocity. So this is the velocity at which the system levels out. That's when we have an equilibrium between the component of the magnetic force, which is acting up the incline, has to just equal the component of gravity that is pulling the bar down the incline. Are there any questions about that example? All right, next one. Go to the other side. This one is a little change of pace from the last one. Instead of changing the area, what I'm going to change here is the strength of the magnetic field. And let's take a look at how that affects the induced electric field. We've actually already looked at this problem before, but now I'm going to look at it again from the standpoint of Faraday's law, and I'm going to tie in what causes the voltage, which is an induced electric field. Okay, so really, what this is showing us, and this is very significant, is that a changing magnetic field can induce an electric field. So we can get an induced electric field just by changing the magnetic field strength. Now that's also changing the magnetic flux. But there's two ways you can change the flux. Remember, you can change the flux as dB dt times the area plus dA dt times the magnetic field. So we've been looking at a lot of examples where the area was changing as a function of time. And so that's what we did in the last example. But in this one, we can get an induced voltage just from a change in the magnetic field strength over a constant area. And so that's inducing an electric field. And that's something that is difficult to show using magnetic forces. Before I showed that this kind of a change in the flux can be related to magnetic forces. But this term isn't. This is something a little different than that. This is a change in B can induce E. Okay, so that's more fundamental and gets to the actual production of electromagnetic waves, because if you have an oscillating charged particle that produces a changing magnetic field, then it turns out that changing magnetic field can induce an electric field, and they can invent each other as they go along. So that's way different than just looking at a conductor that's moving through a conducting rails. This is something that's very fundamentally different. And so let's look at that case then. Here we have dB dt times pi r squared. But we also know that the induced voltage, E, is minus the integral of E dot dl. This is our connection between voltage and electric field. If we remember that the units for electric field are volts per meter. So if we have volts per meter times meter, that gives us volts. So if the electric field is constant over the distance, then this just became EL cosine theta. And if we're moving in the direction of the, we're moving against the direction this way, so we're going this way, a distance L against it, then this angle is 180. And so that just gives us plus EL. So this is the number of volts per meter times the number of meters, and that's the change in the voltage. You know, this could be, say, 100 volts per meter. This could be 2 meters. Then the induced voltage going from here to there is going to be 100 volts per meter times 2 meters, or plus 200 volts, because we're going against the electric field. It's like swimming upstream. Okay, so here, we're just basically doing that same thing where we're saying if the electric field changes along that integration path, then we have to integrate all the different values for the electric field. And so that's essentially the area under the curve. So in that capacitor problem, where we had something like this, that was the electric field versus R, then the induced voltage here is the area under this curve. So this is a fundamental relationship. This is how we define an integral. So in that case, the induced voltage is just the area under that curve, which is the integral of E dr. And so that's how we got the induced voltage in problem 2 on the exam. And then you do Q equals CV in order to get the capacitance. Okay, so that's a basic fundamental relationship. I'm just reviewing that for you. In this example, what we need to do, because the electric field lines are closed loops, is we have to integrate over a closed path. And so this then is our connecting link between Faraday's law and the induced electric field. So this is dB dt times the area, like that. Now, at a particular distance r away, let's say that the magnetic field is going into the board and has a mathematical relationship to the time that's parabolic. So here, if I wanted to plot the magnetic field versus time, we'd start out here at 3, and then it would take off like a parabola from there, 2t squared. And so if that's the case then, using Faraday's law, we can say, well, at some radius r, what's special about this radius r? Well, we'll make it smaller than the total radius of this region in which the uniform or the changing magnetic field is oriented. And let's just see what the electric field looks like as a function of r. So what that, I mean, there's always going to be an electric field there, but if it's an insulating material, that's not going to move charges around. So what you could do then to make use of that induced electric field is to put a ring there, a conducting ring. So this is like what I did with that demo in class. Remember when I put the ring over that long solenoid, and that changing magnetic field induced currents through the ring. They constantly change direction because the magnetic field was constantly changing direction, because the current was constantly changing its magnitude. Okay. But for a simpler problem like this one, we can just say, well, if we're out here at some radius r away from the center of this thing, and r is less than the radius in which the magnetic field is acting, I could put a ring there, and if I did, then the induced currents are going to be such as to oppose the change that produced it. And so what is the change? Well, the change is an increasing magnetic field into the board. And so what we need to do then is say, well, what direction is the electric field going to be? So here, we go this way. Actually, we want it to go this way. We can change that in your notes, sorry. It needs to go this way. Then, inside of this loop, the magnetic field is getting bigger, but the induced electric field is going to generate a current, which is going to generate a magnetic field that will oppose it. So the electric field is going to want to go around in a counterclockwise direction. So my math is okay, but I got that direction wrong. I was doing this morning. I guess I was still asleep. But, so here, if this is the direction of the current, then the current would go around and then it would pop out. It only counts what's happening inside. So that would generate a magnetic field that would oppose this increasing magnetic field that's going into the board. So it would go around that way. Okay. And so, but because we have symmetry in this problem, cylindrical symmetry, the electric field is going to be constant at a given value for r. So we can write this then as E times 2 pi r equals minus d flux dt times pi r squared. And there's also a minus there because this is minus the integral of E dot dr. So we can then divide through by 2 pi r and we get the induced electric field. So the induced electric field has this general expression for a given value of r. Now we might ask, well, why would the electric field go to 0 at the center? And that's what this is showing us. So that the induced electric field at the center is 0, but that it's increasing as we get farther and farther away. Well, at the center, which way can it go to oppose the flux? It's a trick question. Which way would it go, could it go to oppose the flux? It can't go anywhere, right? Because it's in the center. A clockwise or a counterclockwise loop around the center is going to have the exact same effect as it has a radius of 0. And so how are you going to oppose this change if you're right at the center? There's nothing you can do. Well, there's nothing I can do. I'm just not going to generate an electric field there. Okay, so that's why the electric field is 0 here. Why does it get bigger as the radius gets larger, as it approaches big R? Don't we have more changing magnetic flux? If we're going to a greater distance away, then isn't there more flux in there to fight against? Okay, so that is physically, you can get the physical feeling for this. It's a lot better than just getting lost in the equations. This thing is going to try to fight the change that produced it. And so it means that the current is going to get bigger as you get farther away because you have to fight against, it's only the area that's inside that counts here for the change in the flux. And so to fight that change in the area inside, you need a bigger electric field and a bigger current to do that. And so that's why it would look that way. Are there any questions about that basic idea? So this is a completely, it's the same expression, Faraday's law, but it's a completely different application of it. It's this application. Whereas in a lot of the other examples, like the one with the generator, that was this application here. But this application is important too. Especially for understanding electromagnetic waves living around. Okay, so what we've got then, if we take dB dt, we've got, it's not constant because it's a parabolic relationship. And so that's going to be, dB dt is just 4t. And so here we've got r over 2 times 4t. So that means that our electric field is a function not only of the radius, but also the time. because of the way in which the magnetic field is changing. And so if I wanted to evaluate this expression at a particular distance away, say 1/2 meter, and at a particular time, then I would just plug in 1/2 meter here. That would give me 1/4 times the time of 1 second. That would give us 1 volt per meter. And if we wanted to, we could figure out the current too, because the induced voltage is IR. So that means that the induced current would be the induced voltage divided by the resistance to current flow over 1 complete turn. Any questions about that? All right, next, I'd like to do is go to the second handout that I gave you. And I want to look at a little more at induced voltages. Induced EMF, electromotive force, that's what we're also calling voltage, but in the book they call it EMF a lot. It's just induced voltage. Okay, so we already know about this expression. The magnitude of E is equal to the integral of E dot dl. But how does that relate to the velocity of a current carrying conductor? Well, we already looked at that kind of a problem earlier. We saw here that we have a conductor moving at a certain velocity through a magnetic field, then that's going to cause a change in the flux. But we could just do it in terms of forces too. Remember, I solved this problem 2 different ways before. I solved it one using forces, and the other way using Faraday's law. And I showed in that example. By the way, all of those problems from the last midterm are on the videos that are posted. Okay, and so I've solved all 3 of those problems. And you can go back, if you don't remember something, you can go back and look at it. Like if you don't remember that I solved this 2 different ways, you can look at that lecture because it's all posted on the homepage for you. Okay, so we did this, and what we showed is that it was equal to BLV. Okay, so why is that true? Well, let's just look at it one more time, why that's true. Sometimes it helps to go over this stuff a few times. Sometimes it doesn't help. But if we're moving a conductor through a magnetic field, let's say the magnetic field is into the board, then that's going to generate forces on negative charges that's going to be down. V cross B is up. So remember that our force is equal to QV cross B. Okay, so the force on a positive charge would be up, V cross B. So, or you can do it this way too if you want, V cross B. That still gives you force up. I've seen a few of you doing this. It's okay. You know, I get confused because I start turning it around and I don't know where I am anymore. I can always use this and I know where I am. And so that's why I use it. Okay, but with a negative charge, then it's going to go the other way. So the negative charges are going to be smashed down. The positive charges are just going to be bare nuclei, naked from their electrons. The electrons have been left behind because they've been smashed down to here. So it's not that positives are being driven up so much as these negative electrons that are the little lightweights are accelerated 2,000 times more, approximately, than the nuclei. And so that jams these down, but not infinitely, because eventually we get to the point where QE equals QVB. And so at that point, the induced electric field, E, and this is true all the way through this bar, is just VB. But it's really V cross B, right? Because the V has to be perpendicular to the magnetic field for us to get that force in the first place. So this is really the same thing as V cross B. Where the direction of VB is going to be perpendicular to the plane that contains V and B. And so that's where we get this thing. That's where we get this integral equal to the integral of E dot dl, but then we can write that as V cross B dot dl. And so this then is our induced electric field. And so this is just another way of writing the induced voltage. And so let's look at an example other than this one. Okay, so with this one then, basically we could take a voltmeter here, and that voltmeter in this little window then would measure the voltage difference. This would go to the ground side. This would go to the hot side, like that. And it would measure that voltage difference just as if there were a battery in there. That's the same thing as having a battery in there. But you're producing the electric potential with your energy. So when you pull on this thing to keep it going at a constant velocity, you're adding energy into the system. Just as surely as when I was turning that crank and I was getting the light bulbs to light up, I was adding my energy and converting that energy into electrical energy in the form of current. So if I pull on this thing, I feel a drag force. Just the same way as I felt a drag force when I was turning that crank. And so that's where the energy is coming from. It's not coming from nowhere. It's coming from you and your ability to pull on this thing and keep it going at a constant velocity. If there's no resistance, then there would be nowhere for the energy to go. It would violate conservation of energy. Okay, so with that idea in mind, let's look at a slightly more challenging example. This one is called a disk dynamo. So in this problem, let's say we have a uniform disk that is conducting, uniform conducting disk. And we have it immersed in a magnetic field that's out of the board. And so if we rotate this thing with an angular frequency omega, let's find the voltage induced between the center and the outside edge of this disk dynamo. So just by rotating this thing, it's just a conductor. There's no excess charge being put on it. It's a chargeless conductor. But we can still get the motion of charges moving through a magnetic field. Okay, and so this thing has, let's say, some radius big R. So that's the radius of our big disk. And so what we need to do then is think in terms of, well, how is each element of charge going to move? And so it's going to move with an angular frequency omega, means that the velocity at any radial distance r is going to be equal to omega r. Remember, omega is v over r. And that's in units of radians per second for omega. Okay, so that's your number of radians. So 2 pi radians per second is 1 revolution per second, or 1 hertz. And remember, omega is also 2 pi frequency. So what we need to do then is rewrite v in terms of omega. But we also have to do our right-hand rule and see what direction that force is going to be acting. And so if I do V cross B this way, and sorry, feel bad. I do V cross B this way. No, that's right. Because the magnetic field's out of the board, so V cross B dot dr is going to be out that way. So this is going to be my little dr, and V cross B is going to be the direction of the induced electric field. So the induced electric field is going to act up. And so what that's going to do then is that's going to induce a force on charges which are going to make negative charges go this way. Force on negative charges is going to go down because the induced electric field on positive charges is going to go up. This is V cross B dot dr. Okay, so the direction then of V cross B has to be the same direction as the direction of dl. Because when you're figuring out the voltage here, the voltage is EL, in this case, volts per meter times meter, right? So you have to have the integration path, the little dLs have to be in the same direction as the V cross B. So the direction in which the charges are being forced is the same as the direction in which you're figuring out the voltage difference. So, I mean, it's easy to just blindly plug into this equation and not pay any attention to all that stuff. But that's what makes it important. That's what makes it work. And so if we write omega r, then that generates a force on positive that's up. That generates a force on negative that's down. That means that the whole outside part of the ring is going to end up charged positively. Not because positives have been pushed out there, but because the negatives have been ripped away and all jammed down into the center. And so we're really thinking in terms of physically understanding this. We're thinking in terms of what the electrons are doing. Because the protons are going to be accelerated, well, we say 1/2000 as much, because the mass of a proton is 1836 times the mass of an electron. That's really a lot more than that, because you've got a whole nucleus. And the nucleus has a whole bunch of protons and neutrons in it. So it's more like maybe 10,000 times more acceleration rather than 2,000 times more. Or maybe even more, maybe 20,000 times more acceleration on the electrons, because the nuclei hardly budge at all with that same amount of force being applied. Okay, so that's why the electrons are essentially the only thing that's changing the configuration and generating this electric potential. Okay, so we can write this then as omega RB, that's V cross B, okay? But that's in the radial direction. So this is omega R times some unit vector that points in the r hat direction. But that's the same as the integration path dr, as we're figuring out the voltage. So we just pull the omega and the b outside of here, and then we just have omega b times the integral from 0 to big R of r dr, which is just r squared over, big R squared over 2. And so that's our voltage. It's again, there's an interesting geometrical consideration here, that the real math is almost just one step to get the right answer. It's just knowing what is being implied by all of this stuff that takes a little bit of thought and energy to figure out. Are there any questions about that? Okay, so this is kind of a classic problem. It's one that's easy to knock off mathematically, but it illustrates a lot of these concepts that we're looking at. Finally, for induced electric fields, I wanted to look have an alternative form of B cross B, which is a determinant. And I'm going to solve this problem using a determinant. Okay, so in this problem, let's say we've got an airplane is moving north. At, let's say, 100 meters per second. So it's moving north. And the magnetic field that it experiences, and let's say that north is what I'm going to call the J hat direction. The I hat direction, I'm going to say, is across the wingtip. So that's from east to west. So I hat is east to west. J hat here is north to south. And then the K hat direction I'm going to have into toward the center of the Earth. So this is the K hat direction. Why am I doing it that way? And why does the magnetic field just have a J hat and a K hat component? Well, because when you look at the Earth, this is the south magnetic pole here is actually the north pole of a bar magnet. And this switches, by the way. 700,000 years ago, there was a major switch, and the polarity of the Earth's magnetic field shifted. That's different, of course, from the whole Earth shifting. That's not what I'm talking about here. I'm talking about internal dynamics, which cause the magnetic field to change. And so you got all kinds of weird stuff happening, particularly in the outer core. Outer core is mostly made of metals, and so you can have complex fluid motions happening there that can generate a magnetic field. And so they've done experiments with big, huge spherical tanks, and they've rotated the spherical tanks, and they've been able to get magnetic fields inside the reverse chaotically. So this is something that we have a little bit of a feeling for, but not totally. And by the way, these poles can wander too. They change. So the south pole of a bar magnet, which is our north magnetic pole, is actually, it's in northern Greenland right now, but it's on its way to Siberia. Okay? And so we don't know where it's going to go next. It's a little bit of a chaotic wander that it does. But at a particular location, the magnetic field is going to have because it goes from north to south, it's going to have a J hat component, which is toward the north, and a K hat component, which is toward the center of the Earth. Okay? And so if you do this then, and you go into the lab, we have these, we should have probably used them, that we have these dip needle things. And so it's a magnetic needle that points along the direction of the Earth's magnetic field. And so it has a dip angle. And so we can show that in the lab. That it's not just pointed toward the north, like a compass would show, but it has a downward component that also points inward toward the center of the Earth. And so we'll say that we're moving not in a purely northerly direction, but toward the north magnetic pole. Okay, so that's approximately north, but at this latitude, there's something like a 16-degree difference between true north and magnetic north. But we'll assume we're going magnetic direction. And this is the magnetic field. So as we fly the plane north, this is my I hat direction, this is my J hat direction, this is my K hat direction. I want to find the voltage induced between the wingtips. Okay, so here's my conductor. And so what I need to do then is find the surviving terms of V cross B. But here we've got two different components for the magnetic field. We've got one component that is going with the direction toward magnetic north, and we've got the other component that's going into the bore. But the velocity is going just in the direction of magnetic north. So that's got 0 and 0. It's got no components in the wingtip direction. This is going pure north, and it's not diving. So it doesn't have any of the vertical components. And so this is the way you write a vector cross product in terms of determinants, is you write the I hat, j hat, k hat, then you write the different components of velocity, or whatever it is that's the first term here, and then you write for the magnetic field. And so you can do the same thing for force. You can have force is equal to Q V cross B. And then you could write this as the determinant of IQ times the determinant of I hat, j hat, k hat, Vx, Vy, Vz, and Vx, Vy, Vz. And so this is more useful if we've got some random direction and some random orientation of the magnetic field, then you can just do this determinant. And this is kind of in between, because we've got a y and a z component, but you could probably just do that in your head without having to do the cross product. And so that's why I'm using it for this example, because I can also show you that that makes sense physically from what we've already looked at. Okay, so here, if I plug in dy and bz, and v here, we have I hat times this cofactor. That's going to be v times bz minus 0 times by. Then we have this one times this cofactor. And so those are zeros. And we have this one times this cofactor. And those are all zeros. So the only one that survives is the I hat component that goes like vbz. So this is really vy bz, but the y component of velocity is the total velocity. So that's why I'm writing it that way. Okay, and so what we could do then is we could say, okay, well, then it's just vy times vz is v cross b. So let's double check that in terms of what we know about magnetic forces. If we're going this way with vy, and we're curling our fingers into the vertical component of the magnetic field, the one that goes straight in toward the center, that's going to give me a force that is going to push positives this way and negatives are going to go that way. So this is just like, and so we integrate VB from 0 to L, so it's just BLV. Does that look familiar? BLV, that's what we've been getting all along. For all of these different conductor moving through a magnetic field that's perpendicular, BLV. But this is just the Z component here. Because the Y component is in the same direction as V. And so that part cancels out of our determinant. Okay, and so this is the answer then. The induced voltage between the wingtips is the velocity, so that's 100 meters per second, times Bz. So we got to be real careful here. We're using this component. And so that's going to be 3 times 10 to the minus 5 Tesla. Times, and then that direction is in the same direction as the dl that we're integrating. And so that's what we want here, v cross b dot dl. So the v cross b has to be in the same direction that we're integrating in order to get the total voltage along that path. This is BLV again. And so the L then is 20 meters. So that'll give us then, what's this, 2,000. So that's 6,000 times 10 to the minus 5. So that would be 6 times 10 to the minus 2 volts. Or so that's 60 millivolts. So that would be the voltage difference we would get. And these are somewhat comparable values for the Earth's magnetic field. So I think that's a reasonable number that we would actually get for them. Now, what if we wanted the voltage between the head, or the tip here, the nose of the plane, and the tail of the plane? What would that voltage difference be?
0.
That would be 0. Why?
Because it's in the direction that's parallel.
Right, the forces are in this direction, but that's along an equipotential line. Okay, and so the V cross B here and the DL are perpendicular to each other. So you're not integrating along the right path. What about for the Y component? Is that going to help us? It won't work for the Z component. What about the Y component of the magnetic field? We're moving this way, so is the Y component going to give us any magnetic force? Are we going the same direction as this component of the magnetic field? So that means that there's no force, because you're going right with the velocity of the charged particles going right with it. So that doesn't help us. What if you went down like this and did a nosedive toward the center of the Earth? Then could you get a voltage difference between the nose and the tail? Well, then you'd be going with BZ. If you're going straight down, then BY would be this way. So you'd still get a voltage difference between the wingtips, but then this would be the BY component if you were going straight down. But you would still get no voltage difference between the nose and the tail. Okay, so those are the different variations on it. And it also brought in something that I've been wanting to do for a while, which is introduce that idea of the determinant and how that can be used for more complicated mathematical problems. Are there any questions about that? All right, well, the next thing we can look at is our third major type of circuit element. And that's called an inductor. So we can think of an inductor as just being like a coil of wire, but there are different kinds of inductors. And we define what we call self-inductance by big L. And so that's why I've been, as much as possible, controlling myself and trying to use little l for length in a lot of these problems. But self-inductance is given the symbol big L. And it is a measure, it typically is some kind of a coil. And what it does, essentially, is it acts kind of like an inertia term. If you try to change the current through a coil of wire, it resists that. So if you've got a constant current flowing, no problem, because there's no change. But if you try to change the current, it's not going to like it very much. Why? Because as you ramp up the current, there's a change in the flux through each one of those terms. And so there's, as the current goes from smaller to bigger like this, ramping up, there's going to be a counter-opposing change caused by Faraday's law. And so Faraday's law then predicts a back EMF. And so what does that mean? Well, if we've got a forward voltage going this way, then it's going to resist that by pushing back against it. And so it's not going to like that. And so it's going to resist that by generating a voltage here that's equal to minus d flux dt. So it's going to oppose the change that produced it. If the current's going this way, it's going to exert counter-opposing currents. And so this is the source of eddy currents. Remember when we had the magnet swinging through the conductors? Do you remember that in lab? That was kind of a fun thing, and it just was like a magnetic brake.